Hello everyone, my name is Rock, and here's my full name. Today I would like to introduce a paper titled as Automatic Permission Check Analysis for Linux Kernel. And without further ado, let's get started. So in this slide, I would like to share some basic information about this paper. So the title, as you can see previously mentioned, and the publisher of this paper is IEEE Transactions on Dependable and Secure Computing. And the published date of this paper is the 6th of April in 2022. And the citation is 4. And here are some authors. The authors of this paper, some are from some prestigious company like Google, Meta, and some prestigious university like Purdue. And the keywords of this paper is Linux kernel, static analysis, permission check, and bug detection. So as you can tell from the keywords in the title, it's pretty much related to our operating system class. And I'm also currently researching on static analysis, so this is why I picked this paper. So for abstract of this paper, here I list 3 key points you need to note. The first one is that the background is kind of like Linux kernel itself, the source code of it is the code base is pretty huge, so it certainly contains tons of like permission checks. And the permission checks here means some like system calls, they need to check the privilege of the user or process that needs to access some critical resource. So the complexity, since the code base of Linux kernel is still evolving and growing, so the complexity is keep increasing. And the secondly is that the paper proposed you can say a scheme, a tool called PAX. It is a static analysis tool that can detect some permission check error for the Linux kernel source code. And the main task is to identify missing, inconsistent, and redundant permission checks. And lastly is that the tool itself, in this paper, they set a particular version of Linux kernel. Here is the version number, and eventually the result shows that 45 new permission checks that detected the errors detected by PAX. Eventually, 17 out of 45 were confirmed by the kernel developers. So this is kind of like the contribution of this paper, the tool. So before diving into the technical details of this paper, we need to first go over some basic information here. So starting from introduction, the first thing you need to know is that in operating system like Windows, that we usually have several users, right? And different users have different access rights, and that access right is called permission. And for permission, the key concept is that only those who have appropriate permission can access critical resources like files and sockets in the system for some services. And secondly, for access control, that in Linux kernel, some built-in modules here, we have mainly 3 of them. The first one is discretionary access controls, DAC, and the second one is capabilities. And the third one is LSM, Linux Security Modules. We have these 3 to manage access control. And the third point is that since the code base of Linux kernel is that huge, so it's really hard to ensure all critical paths are adequately protected. So this is why we need to care about the permission checks in Linux kernel. And here we have a table here, as I mentioned that there are 3 types, and here are some examples of their permission checks system calls. So these displayed here that you can see, they are all system calls. So subsequently, we will introduce each of the access control type that discussed in this paper. The first one is DAC, discretionary access control. And so for DAC basically restricts the access to system resources, and is especially for files. So the idea is kind of like in operating system, we introduce access control list. So in that kind of design, we can use RWX and some number to represent the privilege upon a user towards a file or group or others towards the files. And it has three permission like read, write, and execution. So in Linux kernel, DAC is kind of like is in charge of that policy. So in Linux, every user has a user ID, group ID, and files have permission bits to define whether a user or a group can read, write, or execute a file. So this is basically what DAC means. So in previous slide, we use access control list to explain what is DAC. And in this slide, we will actually dive into what Linux kernel module uses DAC in the source code sense. So in Linux, there is some, you can say, built-in function. It's called inode permission. And it's basically used to check the permissions of current process if the process has a privilege to do something. So, but this inode permission is basically a wrapper of POSIX ACL permission. So judging from ACL, this is the function actually performs the permission check, but the wrapper, which means that inode permission, is basically maybe like a package functions that packs this function and to conduct the permission check to check the process actually executes this has the privilege or not. And as for the experiment in this paper, like before the version 2.2, Linux kernel uses a separation of normal users and super users. So it's a binary. It's either root or normal user. So in some cases, if you have root permission, basically you just bypass all the kernel permission checks. So this is not a good practice and a problem. So here we have some images here, like I demonstrate, like if you don't have permission on some files, you and you try to read here, you can see that you have permission denied. And the second one is that if you simply has the root, like you log in as a root, or you just do the privilege escalation, become the root, then you can simply just access the file you want to edit. Like here we have sudo nano. You either just do a temporary escalation, or you simply log in. These both will work to modify or edit a file that is requires higher privilege than normal user. So previously, we introduced stack in the higher level way using access control list to explain. But here we are getting deeper to actually look at how Linux kernel is defined and use its built-in source code to do the access control. So the second one is capability. This is basically a fine-grained access control which divides the root privileges into small sets. What does that mean? So generally for root, it can almost do anything, right? But for capabilities, it has some labels here. We have like capnetadmin. So basically it means that the users which has this label, you can use pin without granting the full root privileges. So in some versions of Linux kernel, like 4.18.5, it supports 38 capabilities, including like capnetadmin and capsysadmin. So each of these label, it represents actions that allows the user to do. So here we have some images to explain this concept. So here we run the Docker. The Docker runs a system Ubuntu 22.04. So it's running a operating system. So inside this container, we run the pscap command. So you can see some process here represent each service that the process is currently executing. So here we can see which user is accessing. So here we have root to root, but you can see the last root here we have the full capabilities, which means it has complete privilege as doing everything upon this process level. But here we have another root. It has several capabilities labeled like deck override, deck read, and something. This means that even though you are root, but you cannot do everything in this process level. So this is why capabilities enables that the access control is no longer binary, like you are either root or user. Even if you are root, your capability is still limited. So now that we know what is capabilities and why we need it to do access control, but we still have got tons of issues need to face. Firstly is that we know that Linux kernel, the community it really doesn't have a clear scope definition about the choices of capability labels and when to use which one. And upon those privilege functions that defined in the Linux kernel source code, is really subjective, like those kernel developers' own understanding to use which capability label. So, but unfortunately, we have tons of services that hosted on the operating system we need to use. But all of these tools overuse a label called capsysadmin. Basically, this label, this is not fine-grained enough, but because if you use this label, basically you just grant the whole coverage of privilege. Basically, a process, if a process has this, it can do anything. And so in the operating system, almost 38% uses this label to because they need a privilege to conduct some operations in the operating system. Like we have some like if config, IP tables, mount, unmount, and cron and syslog. All these tools need capsysadmin because usually you'll need to do some I/O operation or networking. These process usually would requires a root or some higher privilege to do in the system. So several tools overuses. This is the problem that we need to face. So the next access control policy, we have LSM, Linux Security Module. This is a really unique module in Linux kernel because it is not a part of it is not actually hard-coded in the Linux kernel source code. It is pluggable hooks. So this means that if you need it, if you need certain access control, you can just plug it in, and if you don't need it anymore, you can just plug it out. And in this kind of design, users can customize the permission checks if callbacks if the user needs it. And the last thing is that this module has a concept of mandatory access control, MAC, in Linux. It has some packages called SE Linux and AppArmor, and this different kind of package, or you can say library, you can use it to under the ground truth of like DAC and capabilities, it has a higher priority, like is a top priority, stands upon the previous two access control lists. It is strict, even stricter, and even more fine-grained than the previous two, and is non-overridable once it is plugged in the access control policies. And here are two examples of implement LSM. Like we can use AppArmor to focus on the file system, the file access control, and we can use SE Linux to further control like networking or even some I/O operations that is deep inside in the operating system capabilities. In this slide, we have another example to explain LSM how it works. So let's suppose a process tries to read a file path of a symbolic link. and in Linux kernel, it has a function, built-in function called security inode real link, and that will be invoked, be called, and to check whether the process itself has a read permission to, upon the symlink file. What is a symlink file though? You can think about that in Windows system. We can easily right-click a file. Like here we have an example. Maybe we right-click a Chrome web browser to create a shortcut, and it will easily be created, and we can use it to open web browser. And in Linux, however, we can also do that, but we need to use command like ln here. You can basically create, like, here's a txt file, and we can create a shortcut for it. So when anytime you access this file, it will point to the actual file, the content, so you can read the same content of that file. But like system like Linux, we usually have several permission checks, like your privilege. So for here, if you don't use LSM plugin, like all the permission checks, access control of LSM, we have a plugin, right? If you don't use it, like there's a missing hooks placed at security critical point, like let's suppose this file is confidential, but you don't plug in the LSM, it will directly be read and without permission checks. Like, so this is the issue that for LSM, if you don't plug it in. So now that we know all of the three access control methods in Linux kernel, but now we will focus on another issue called permission check errors. So in this paper, it proposed PEGs, and some of the Linux kernel developers, they noticed them by manually. But before actually see what is the errors in the sense, we need to first understand two concepts. The first one is permission check. So, and another one is privilege functions. So what are them? So for permission checks, it basically means those functions that validate whether a process, like a user or group, has the proper permission to conduct certain operations. An example like it will be checked if a user want to do app install, but VBox user or user 2 usually does not have the privilege to do that, but root can. So it's focused on the user. And the second one is privilege functions. It represents the functions that only a privileged process or user can access and require permission checks. So example, like if you want to format a disk or delete a file, these functions will check if the permission to check if the user has the privilege. So these two things is highly related, but permission checks is focusing on the user side, the caller, and the privilege function is focused on the callee, the functions that is being called. So in this slide, we will be introducing what could be permission check errors using the three of the images example from the paper, from A, B to C. But before diving into the details, we need to first clarify the relationship between these three images. So firstly, in A, we have a function called SCSI IO control, and in B, we have SCSI CMD IO control, and in C, we have two functions. For the first is SG SCSI IO control, another is BLK verify command. So back in A, we can discover that A call the function from C, SG SCSI, and also in B, it also calls the SG SCSI IO control from C. But in A, before calling this function from C, it has two permission check. One is CAP SYS admin and CAP SYS RAWIO. These two permission checks. But inside B, there's no any further permission checks before calling this. So this is the inconsistent when calling these same method in different function, and this is the inconsistent and could be a problem of the permission checks. So here we have two possibilities. It is either that inside A, it has a redundant permission check of cap sysadmin, or B, lacks of the permission checks that the A do. So we have two possibilities, but we don't know which is the right one. So this slide pretty much summarized what we discussed in the previous one-page slide. And these are the check errors conclusion from the paper. Like when it comes to the SC, SI, IO control checks, this is the first function from image A. It checks these two permission checks. And second point is that, but the B function, SCSI, CMD IO control only checks cap sys WAD WIO, and this is from because B also calls the function from C, and C inside the C it has another function has the permission check of this. So is either this image B function missed the permission check, or the first A image has a redundant check of this cap sysadmin. So, but we don't know though. So this is the problem, that when PAX detects this bug, because of this inconsistent, of course it will be detected, but it still remains unknown that how we can resolve this problem. Next, in chapter 4, we will introduce some challenges when this paper trying to detect the permission check errors in Linux kernel. The main two issues will be, like the first one, indirect code analysis in kernel, and the second one is the lack of full permission checks, privilege functions, and their mappings between these two. So inside the real-world Linux kernel source code, we will see several practices of indirect calls. The first one is the frequent use of indirect calls. It's like because we need to achieve modularity and flexibility to scale the Linux kernel code base. So there will be tons of indirect calls, like some function pointers as the arguments or parameters towards some other functions. So this is it increases the complexity. And the second one is the kernel abstraction, like some of the services that defined by Linux kernel, like virtual file system, VFS, it provides a unified interface. Like for example, there's a file operations in VFS contain some function pointers for file-related operations like write-iter or read-iter. So for VFS, you will accept some types of function pointers like write-iter or read-iter. So even in some complete implementation like VFS, it still has a abstraction using several function pointers. So here we have two figures from the paper. The first one is A. So you can see here is a struct called file operations, and it has two operation called read-iter and write-iter is a function pointer. So it's literally two indirect calls. And here we have B figure. It displays that so we will have some methods like write and syscall, and these two are functions, but from user space doesn't require some special privilege. But we will have tons of kernel space functions, like for each service. Like we have syswrite, this is one type of write, and we also have VFS write, this is another type of write, but they could be all implemented in the same same methods. Like here we can see in these two, like we have an implementation of ext for file operations and nfs file operations. Inside these two function definition, it all has like a mapping of .read-iter to assign to ext for file read-iter. and write iter to assign ext file write iter. And in NFS is the same way, like the same two functions are just assigned to a different name functions called NFS file read and NFS file write. So inside them, they could be the same methods implementation, but in the different ways of permission checks in further implementation. So this could be the complexity that abstractions increases. So as for indirect code analysis in kernel, what could make it difficult? Some challenges that mentioned in this paper. This paper specifies a version of kernel 4.18.5. It has 15.8 million lines of code, which contains 247,000 functions, and almost half of them contains indirect code size. So this makes it difficult to traverse all the different paths of this source code. But we of course have some traditional static code graph analysis tools like SVF. This is a well-known GitHub repository, has several stars here, but it is hard to use this kind of tool to scan through the huge code base for kernel. Like previously, like in this paper, and conducted an experiment to use SVF to scan the Linux kernel, but it is out of memory on the 256 gigabytes machine when analyzing the whole kernel. So we still need to find out other ways to get around this. So in previous discussion, we know that for indirect code analysis in kernel, if we use some tools like SVF, it could run out of memory and could not proceed the analysis. So in previous literature and also this paper, conduct a method called type-based approaches. But it turns out that is imprecise because we have some examples here. Like here at the bottom, we have the image. We have two functions that we mentioned before. One is read iter and write iter as a function pointer. These two functions point to the same function type. They are all function pointer. They are the same type, but this is the problem. This is the problem because if we use the type-based approaches, it will recognize that they are the same, even though they are different two-purpose functions. And another one is that if we use SVF, it can resolve this problem because it's basically traverse the paths, but it's unscalable as we mentioned. It cannot analyze the entire kernel. Turns out to miss targets, so the problem still remains. So far we mentioned so many problems that could happen in the issue of indirect code analysis in Linux kernel. This paper proposes a solution called PAX, a tool, and inside this tool it has a component called Kirin, which stands for Kernel Interface Based Indirect Code Analysis. And this tool, it basically leverages kernel abstraction interface to improve the precision and the scalability. And it also focuses on 90% of the 95% of the indirect calls from kernel interface. Here's an example to explain how it works. So for example, we have a function pointer called write iter, and this function is assigned to another maybe a higher level function that calls ext for file write iter, and Kirin will map these two to have a relationship mapping between these two to resolve the problem of needing to traverse all the paths, and with this mapping can resolve the problem. And how this mechanism resolves the problem will be further discussed in detail in chapter 5. So we finished introducing the first issue 4.1 indirect code analysis that this paper proposed tool PAX will face. This part we will introduce the second one, which is the issue about the lack of full permission checks, privilege functions, and their mappings. So we'll mention mappings before. Why we need that is we need to recall the concept of in the Linux kernel community, it lacks the explicit documentation to specify the scope of which permission checks we need to place and where we need to place them to protect the privileged functions, right? So we didn't mention that the permission checks has wrappers. So wrappers, as we discussed before, is that maybe a higher level functions needs another functions that actually do the job, but the functions can be reused in different services. Like here we have an example. Like there's a function called ns-capable. This is a wrapper for the lower level security capable function. This low level function actually do the job of doing the permission checks. Like here we have a flow chart. Firstly, we maybe have a namespace called init user namespace, and this namespace will cause ns-capable to checks the permission, but actually inside this function we have security capable. So you may see security capable in many parts of the different functions, but in this case this function is wrapped by ns-capable, and ns-capable is the wrapper of security capable. So in chapter 5 we will discuss Kirin in detail, which is one of the components of PACS. So Kirin will focus on the indirect call analysis problem. And another problem about the mapping between privilege function and permission checks will be handled by PACS, the tool proposed by the paper itself. So Kirin is a precise and scalable indirect call analysis technique designed for the Linux kernel. It is built on LLVM framework, and you will analyze function pointers to find out the indirect calls of them. And what if PACS without Kirin? If we don't have Kirin in PACS, then you will cause that the incomplete analysis of permission checks and security vulnerabilities. But why would that be? For security vulnerabilities, let's suppose that if we have several wrappers that wrap some low-level functions, several wrappers could use the same low-level function, but we need to both insert the permission checks between for all the wrappers and the low-level functions. If we don't do that, we don't divide the indirect calls and the actual calls itself. Sometimes it will cause unauthorized access, and that will become the huge security vulnerabilities in the Linux kernel. So that's a problem. And for the Kirin, the workflow of Kirin, it has some foundation. Like it has mainly two parts to conduct. The first one is target collection for the target wrapper and indirect calls, and also find the call site of the indirect call. So with these two steps, we can find where are the indirect calls. And upon this foundation, we will be able to refine to make the path clearer. So when Kirin has done its job to further put the refined result to PACS to detect the permission checks and the privilege function mappings, it will be easier for PACS and more precise for its permission checks errors. So in this slide, we'll introduce some steps that Kirin conducts to collect the indirect code targets. Firstly, Kirin will scan through the source code of Linux kernel to find all the statically initialized structs and find the checks that we can map the function pointer with some specific functions that wraps it. And here we have two examples from the paper. First, we look at image A. So for the first line, we can see that the higher level implementation of file operations called ext for file operations. it is assigned to constant called struct file operations, which is the lower level implementation. And we can see the line 6 and 7, it assigned a ext file read iter and ext file write iter to lower level implementation. So this is kind of like how how the Kirin maps higher level implementation and lower level functions. And image B is another case. It's like here we can see from line 2, here's a write iter I, which represents it is assigned to a get element pointer in bounds. Is using the offset of write iter, trying to map this write iter functions to another function, another higher level function, and the higher level function is not clearly stated here, but we can see here we have %25 and %26 as the register register representation, and this is the syntax of the LLVM as the intermediate representation. Although we don't know which higher level function use it, but we can see here it's basically using a higher level implementation stored in 2 registers to assign it to a lower level implementation function. So this is basically how Kirin reads through, maybe compile the Linux kernel source code and to target the indirect call in the source code. So for indirect call site resolution problem, there's another problem called the usage of macros. So when it comes to using the macro in the Linux kernel source code, it might lose the type information when it comes to compile it to LLVM-IR. Here, let's look at the example. So the original implementation of the source code is the image A and B. For image A, we can see here's a struct USB driver assignment to a function pointer driver, and here's a indirect call site, because here we can see driver that here we call at the line 2. Here's a retval equals to driver.unlock IO control. So it's using the driver indirect call towards the definition of the struct. So this is clearly an indirect call. And the original of the definition of the macro that we mentioned here is a container of. That here's the definition. So inside the macro, we have the assignment of the type void, and here inside, after the computing of the void, it's because macro is just replaced by another name of the variable. So in the end of this definition, we will have an unlocked IO control offset method that get the offset and eventually add the pointer, but there's no clear specification of the type of the variable. So in Kirin, when it comes to this kind of macro usage problem, it uses methods to redefine the macros to preserve type information and resolution of the function pointers. Here, for image C, we can see that the definition of container of macro is changed. It firstly specifies a type function pointer res, and the void assignment remains the same, but here we have the offset and of the type and number arguments, and here we have a memory copy to store the information here for better handling. And here at the last of the unlock IO control, we clearly specify is a struct of USB driver here. So So for the modified macro, it clearly specified the type. So after computing, it will definitely be a struct. So when querying it's detecting the indirect call site, it will directly target it and find out the actual type of this macro without the problem of dynamically assigned type, because since this is not a dynamic but a static analysis. After finishing the discussion of indirect code analysis, we will further discuss the permission check mapping with the privilege functions. So here comes the PAX tool. So this PAX tool, as we mentioned before, it mainly detects missing, inconsistent, and redundant permission checks in the Linux kernel source code, and it will maps permission checks and privilege functions. And as for the input and output of this scheme, or you can say a tool, it will first take source code of Linux kernel as the input, and it could optionally also check the permission macro patterns. Like you can also take cap or may something macro as the input. And the output of PAX will usually be the lists of errors in permission checks, like find some redundant or missing permission checks, and mappings between permission checks and privilege functions. So let's look at the actual architecture of the PAX tool and how it is handled through the whole process. So the first, here are 4 points of the what actually PAX produces. The first is it will produce interprocedural control flow graph, a graph for the control flow of the Linux kernel source code. And the second is the permission checks for DEC capabilities and LSM. These 3 types of access control methods that we mentioned before, and also detects the wrappers for and maps the privilege functions. And the last one is identifies missing, redundant, and inconsistent checks in kernel PAPs. This is the ultimate output. So to achieve these 4 key points, here we have a figure 6 to illustrate the entire process. So as we mentioned before, the input of the source code will be here, indirect code pointer analysis. And the second stage, we will have a code graph generation, partitioning, and the automatic permission check detection. These 2 will be conducted in parallel. So generally, the permission check wrapper might complete first, then we will have the first output, which is the permission checks to target them. And the second output is a privilege function detection. It will also come out as the second output, but not yet. Here we will put them into the put the privilege functions that detected to the non-privileged function filter, which means we'll have a list to filter it out. And after that, we'll finally get the second output here, privileged functions. And this is kind of like a continuous process, because after we are having these 2 foundation, we'll use these 2 to map them to find out the permission check error detection, which is the ultimate goal of the whole PAX process. So next in this slide, we will discuss a little bit about code graphic generation and partition and how it constructs. So for PAX, it will generate a code graph which contains edges, including direct and indirect calls. So this is why we say that the PAX is a continuous process, because we need Kiran to has done its job well, so we can divide the indirect calls to make the code graph complete. And as for the code graph generation, we also need to filter out some non-privileged functions, which is we will target some places like user space, entry points, and those functions that use only during boot, and we will consider it redundant permission checks, and some are not, or maybe potential permission check errors. So in this paper, it also proposes a technique of automatically detect the permission check error detection. And before diving into the details of that, we will here's a refresher of the whole workflow of PEX. So it starts from code construction and followed by permission check detection and followed by wrapper detection, and we will have privilege function mapping. And with all these 4 steps, we will be able to do the permission check error detection. So for the actual PEX tool permission check detection, since we have 3 types of different access control methods, such as DAC, capabilities, and LSM, we of course have to discuss them separately. But for the case of DAC and capabilities, we can discuss them together. Here we have examples. Like for DAC and capabilities, we have some target features, like if the usage of macro in Linux kernel source code is identified, then it will be firstly marked as the basic permission checks. If they take macro related arguments like mask or cap, or they contain comparison instructions or some mathematical symbols like and or equals symbols. Here we have 2 images for explanation. Like we have several already defined macro here. This is the definition part, and the image B represents a combination of DAC and capabilities. Here we have a function called generic permission. This is that kind of function that could be used for DAC access control. And inside this function, we have a macro in the if conditionals. Here we have a mask equals made read, which is a macro. And we also can see that cap DAC read search as the permission check of capabilities. So this example is a model example, like the combination of DAC and capabilities examples. And this is how PEX detects the permission check in the case of DAC and capabilities. So here I provide some basic information about how the PEX tool proposed by this paper used the mechanism to detect the permission check errors on DAC and capabilities. So here we have the algorithm 1 provided by the paper. This is the maybe the algorithm inside the tool itself, and we will also have the detection mechanism of the LSM as well. And here we have a table 2 also provided by the paper. It basically shows you the distribution of the permission check detections. Here we have all checks, and inside all checks, it contains basic checks and detected wrappers. And it differs in different settings like DAC, CAP, and LSM. And these 2 experimental settings, like defconfig and allies config, will be further discussed in the later slides. Next, we will discuss how LSM conducts the permission check detection, its mechanism. So different from DAC and capabilities, LSM is partially relying on the Linux kernel defined functions. It also has pluggable permission checks, remember? So for LSM, it will basically use 3 steps to find the permission checks of LSM type. The first step is to traverse the existing permission check structure in kernel source code, but specifically for those that related to LSM, such as SE Linux and Apple Armor. And the second one is to collect all the register hooks that associated with the callback functions that you defined as the new permission check function. And the third one is to mark those callbacks function built in the Linux kernel as the basic LSM permission checks. And in the next slide, we will discuss it using an example. So in this slide, we have an example from the paper. So in this figure A, it has a source code of several callback functions, including here we have static struct, security hook list, setLinux hooks. We can clearly identify that setLinux is one of the LSM mechanism. And here we also have here is a security key permission, and this is another function that takes our new defined permission check function called security hook heads. Inside this function, we have a key permission as the argument, or you can say the parameter. And in both security hook lists, the Linux hooks, inside it called the key permission. And this is the macro inside this function. And inside this security key permission, they also call the key permission as the argument parameter to call the call-in hook, the built-in Linux kernel macro. So both here the call-in hook and here for the setLinux hooks, we have LSM hook in it. These two will be marked as the basic LSM permission check functions. So after finishing introducing how PAX detects the permission check detection of the three DAC capabilities and LSM, we will also need to know about how PAX detects the wrapper inside the three types. If you still recall, we need to construct a code graph of the PAX throughout the PAX workflow. And in the code graph, you will have different levels like higher level privilege function and lower level function that actually do the job of permission checks. So this is why we need to detect the wrapper inside the three of the types. So to clarify this, we will have to look at some of the features of the wrappers. So for wrappers, you will either invoke basic permission checks or pass the parameters, and this is a key to further discuss the two categories, which is inner wrappers and outer wrappers. And inner wrappers basically performs lower level checks, and outer wrappers basically pass the arguments such as macros of some permission checks, which means outer wrappers are usually higher level and inner wrappers is just lower level permission checks. Here in this slide, we have an example from the paper, which is figure 9. So this example will clearly displays the difference between inner and outer wrapper example. Inside the first Boolean, here we have a capable WRT inode UID GID. Inside this, we have the some permission checks which are lower level, like NS capable, and it contains the cap as the macro, which stands for the capabilities permission check, which is a fine-grained permission checks. While in another permission function, NFS permission, inside this function, we only have a permission check called generic permission, and it's using inode and mask. Although these two are also macros, but these are high level. Like for these two, if you remember, they are basically used for DAC permission checks. So this is higher level, and the previous one using cap is a lower level. So here we clearly divide them into two. Capable WRT inode UID GID is the inner wrapper example, and the outer example is MFS permission, which is this one. For the next part, we will discuss how packs detect privilege function. And we also mentioned before that the privilege function detection in packs is called dominator analysis. And the term dominator analysis is basically describing the relationship between permission check and privilege function. So the dominator is basically the role of permission check because it is used to dominate, to protect the privilege function. So if a permission check, it precedes a certain function, it will be the dominator. And function dominated by a permission check will be called privileged. So the process of the permission check will be 3 steps. The first step is to identify all the call sides of invoking the permission check, which are those privileged function, place, and the dominator analysis will be used to find all the call instruction dominated by the check, which means to find using the dominator permission check to find all the privilege function. And the third step is to mark the call list of the instructions as privilege functions, which means those privilege functions that are preceded by the permission checks. And in this slide, this is the information from the paper. This is the algorithm for privilege function detection, just for your reference. So now we know how PACS detects privilege function. If you still recall, previously we mentioned there's a thing called filter. So the filter has 2 features. The first one is that it uses heuristic-based filtering. This basically means that it's a role-based, the roles that can be defined by the user. And the filter list, it contains tons of kernel library functions that could be excluded because some functions are obviously not a privileged function, like some functions only invoked when the the system is rebooting or booting. And those excluded those list of functions will just be excluded to increase the performance. And the second feature is conservative approach. If the filter list itself will be kept as a small list, and also the flexibility is that users can add some functions in the list when needed. So finally, in this chapter 6, we will explain how PACS conducts the permission check error detection, how it comes out with those results. So for this part, we have 2 mechanisms, or you can say situations and error categories. So for the first one is it will conduct on user space reachable functions. Basically, it will analyzes the paths from user entry points, such as system calls to privilege functions, and you will check whether permission checks precede privilege function calls. And the categories like missing checks and inconsistent will happen in this situation. And for kernel initialization functions, however, it will identify redundant permission checks, like search for those functions only invoked during boot, and this will be the redundant checks. And the categories we'll quickly go over. Missing checks means it without the required permission check when it needs to. And the second is inconsistent checks, that when the same privilege function is called, but different types or patterns of permission checks, like the number of the checks different or something. And the redundant checks is that when unnecessary checks or some multiple times the same permission checks called will be the redundant. And this is the last part of chapter 6. This is the algorithm of the permission check error detection for your reference. Next, we'll introduce the paper implementation on the evaluation metrics. So here we have some PACS detection environment. is built using LVM and Klein, these two tools, and it has two versions. So if you remember, there's a default and an automatic version. The first version requires user-provided permission checks as the input, and the second version is automatic. So it will automate the permission check detection upon DEC capabilities and LSM. And the second part is that PEX resolves 86% to 92% of indirect call size with Karen, and it detected 45 permission check errors in Linux kernel version 4.18.5 with 17 confirmed bugs by developers, as mentioned before. Here in this slide, we will introduce the evaluation methodology of this paper. And as we mentioned before, in this paper, we have two configurant settings. The first one is the def config, which means is the default kernel configuration of the Linux kernel with some commonly used features. So it means that it does not turn on all the privilege functions and permission check functions, and is a smaller code base for standard evaluation. And the second one is allies config. It's basically all non-conflicting kernel features enabled, which means it's basically the source code of the whole huge Linux kernel code base. So this is also a stress test towards the PEX tool proposed by the paper and other tools for comparison. And here we have the environment of the hardware, just for your reference in this paper. In this page of slide, I will provide you with some basic information about the inputs of the PEX in this paper. So as we mentioned before, we will have a version of user provided. So user just provides some customized numbers of DEC capabilities and LSM permission checks for detection, and automatically detected is just simply the whole Linux kernel privilege functions and permission checks functions. So here is the statistics, as you can see, for both def config and allies config. So in this slide, I will introduce the evaluation matrix of Karen, which is highly related to the indirect call analysis detection. And so the first metric is the percentage of ICS resolved. This is basically means the number of indirect call size successfully resolved, and in percentage, the higher the better. And the second is average targets per call site. It means the precision of call site resolution. The targets numbers, the fewer, the higher precision, because the mapping between indirect call and the actual calls, lower level calls functions is usually a mapping. So the mapping is lesser, which means it's more accurate for the detection. And the last one is analysis time, simply means the analysis time cost during the analysis process. And eventually, in the result, as can be seen for the table 4, Karen can balance the precision and scalability, outperforming K-miner and type-based methods. K-miner is another static analysis tool, mainly focusing on the privilege escalation vulnerabilities. So the concept is a bit similar. So, but for type-based, it's a completely different concept because it only detects the type of the function. So in some text like average target, it just fails so hard. And for the K-miner, however, it did not successfully finish the whole analysis because of the code base of the whole Linux kernel. But the Karen can finish the whole Linux kernel code base. So this is a good sign. So after clarifying the input statistics and the Karen matrix, we can finally look at the PEX result of its evaluation matrix. So for PEX, we already mentioned that it has two types of the configuration: user-provided permission checks and automatic detection. And inside the matrix, we have mainly three metrics. we have a privilege function detected, the number, and the warnings reported, and real bugs confirmed. These three are all in numbers, and we will show the evaluation table in the future slides. So finally, in this slide, I present with two tables from the paper to display the detection result of PEX tool. And for table 5, it shows the different indirect code analysis tools such as Kirin, the PEX has, and type-based and K-minor, these three. And in the table, we can see data like DEC capability and LSM and bugs detection. And I have summarized the data insights here. The first is that K-minor with the least warnings but least bug detected. And for the allies config with a bigger Linux kernel size, it even with no available detected bugs because it times out because of the huge code base. It cannot handle it. And for the second is type-based. It shows the most number of warnings, but the same numbers of bugs with Kirin. And the third one is Kirin with the most bugs detection and the relatively low warnings comparing with type. Because this shows a little bit inside of that Kirin can shows a balanced result comparing to type-based method and K-minor. And table 6 shows the ultimate detection result upon the two settings. The one is user-provided permission checks and automatic detection permission checks. So you can see the numbers of input checks, detected wrappers, privilege function detected, and so on. So in this slide, it shows the ultimate evaluation metrics all conducted on PEX, but I see this is a pity because with only these numbers, you cannot actually tell the insights on the statistical results of PEX. And this problem will be addressed further in the rest of this section of this presentation. So next, in this slide, I will go over some of the limitations and future work stated in the paper. And so for the current limitations of the paper, the first one is incomplete invalidation of detection results. So this basically means that the paper mentioned there's no official documents that specify the scope of permission checks and privilege functions. So it means that no one tells you where to put the permission checks on privilege functions, so there's no ground truth to examine their detection results. And the second one is imperfect coverage of privilege functions. So as can be seen in this paper, using the privilege function oriented approach to find privilege function and check those permission checks, but the paper says that another key point may be to target its critical resources. So if the aspect of critical resources can be involved, it will be more comprehensive. The current structure could miss some certain cases of permission checks. And the future work, as can be seen for the second one, is the continuous point that the paper says is better to identify the critical resources, and this is the future work idea. So the last part of this paper is the conclusion. So here are mainly 3 big points about this paper mentioning its contribution. The first one is proposing the PEX framework to designed for detecting missing consistent and redundant permission checks in Linux kernel and actually conduct experiments. And the second part is implements Kirin, which is a precise scalable indirect code analysis for PEX to detect the permission checks errors. And the second big part is the comprehensive permission check detection. It basically tells that it successfully identifies stack capabilities and LSM checks to classify them, to categorize them, to to further identify the wrappers so that it can refine the permission check errors process. And the last part is to mention the impact of the paper, which is mentioned several times, that 45 permission check bugs is further confirmed by Linux kernel developers, 17 out of 45. And finally, this is the last page of this presentation. I would like to share with you some of my personal feedback on the upsides and also my challenges towards this paper I report this time. So let's start with the upsides first. I think this paper is novel and relevant to the real-world use cases because the first point is that this paper introduced Kirin for indirect code resolution, which is very important to refine the PEX permission check errors analysis and to make this whole process feasible and make sense. And the second point is that this paper actually tries to address the long-standing challenges on Linux kernel security, focusing on scanning the source code, since it's a huge, big, complex code base, and some tools like Kminer and type-based fails to detect the security vulnerabilities on the whole Linux kernel code base. And however, the second part is the challenges to this paper. The first challenge I would like to say is there is no further metrics to justify good or bad on numbers of PEX detection. If you still recall the table 5 and table 6 in this paper, it always see from those tables data that the PEX evaluation metric is that the robustness of the tool is pretty good and scalable by the numbers of detection, but it is not objectively evaluated through metrics such as confusion metrics, in the sense that all we see is those numbers, but we cannot tell from those numbers like it is good or bad, because we cannot simply define the warnings, the numbers of warnings. If it is a lot, it is bad, or is it good? And even it has DEC capabilities and LSM, these three types of methods, we cannot really tell just judging from the numbers. Instead, even we don't have the ground truth of the Linux kernel source code, like where to put the permission checks towards those privilege function, but we can still use confusion metrics like to examine, are those numbers like seeing the false positive or true positive, these kind of ideas, these concepts, to see if the detection of the PEX performance is legit. So the performance of the PEX detection is lacks in this paper. This is such a pity, since this huge experiment is conducted but not well examined. And the second part is that the definition of def config in evaluation metrics of PEX is not clear. So the paper mentions, like for table 6 and table 5, the paper says it has two environment, right? Def config and analyze config. But for the def config, it says that those Linux kernel modules are commonly used kernel functions and makes it smaller for the evaluation, but it is not stated in the paper what are they. Like the transparency of the def config setting is not enough, and we cannot really tell, like just judging from the def config is a smaller code base, so it detects smaller numbers of the warnings or detected privilege function and permission check errors. Is it bad or good? We really cannot tell just from the numbers. The transparency remains critical. And the last part is the lack of quantitative comparison with other tools. So as far as I'm concerned, I do some literature review of this static analysis on permission check bug detection. So I found some paper uses some technique like machine learning and deep learning, but this paper also does not mention and did not compare with the results with state-of-the-art methods of static analysis domain. So I think this is also a point that can be improved in this paper. And I think this concludes the whole presentation of today. Thank you guys for your attention. Bye bye.